Welcome to the 7th European and Asian and African online meetup. I'm filling in for Kai and will co-host from now. My name is Christian Werner. I'm not sure people from the Slack will probably know me. And today we will hear about one-shot learning. Really looking forward to that one. And Sam will present that paper later. So again, apologies for the confusion with the starting time. Apparently we messed up with the European summertime and had a defect in the reminder. There will be an update briefly about how we proceed from now on, but for the moment, I hope most got the note and could join. Our schedule for today, as with the previous meetups, just the same. After the brief introduction, we will do a bit of community discussion and then go to the main topic, the presentation, and that's going to be roughly like half an hour, followed by a Q&A, and then we will wrap it up. So not sure how, Sam, how you want to handle questions. Should people wait till the end, or you're happy to take questions in between?
Yeah, I'll prefer to take question in between. Okay,
cool. So we do that. I guess most of you know about the schedule. There's a monthly meetup basically, and in May we already have the next one scheduled by Philip. That's going to be about prototype-based classifiers in the presence of concept drift. I'm not quite sure what that's about, or looking forward to that. And in general, if you're happy to take one for the team and basically also want to present, we encourage you, just reach out to us, Kai or me, on the Slack channel or via LinkedIn or any other means. And it's really nice experience for yourself. If you're starting out, that's fine as well. You don't have to be an expert on the topic or the paper. Just read it, try to make sense of it, and then present what you think about it. And like I did it, Kai did it as well. It's really not super much effort. Just pick a paper you like and try to present it to the audience. And if not everything is clear, that's fine as well. We will discuss any open topics. So if you're eager on doing that, just reach out. Not sure which slots are taken yet, but Kai knows, and just propose something and we will find a date, I'd say. Maybe a brief update on how things are going for the study group. The Fast AI study group, part 2 is underway. And we had the second session. Next one is this Thursday, so they shifted the date as well. It's pretty intense, I have to say, but it's well rewarding. So for people who missed out on this one, you can look forward to it going public. It's really much more. It's very different to part 1, and it's much more bottom up and really into the details. But it's pretty good. I really enjoy it. For handling this this meetup here, I guess I will mute most of you or all of you, and then if you want to ask a question or if you want to speak up, just unmute yourself so we keep the noise down, basically. Yeah, and if there's any other inquiries or questions, or you're unsure about stuff, just ping us on Slack. And you can also use the chat within Zoom. I'll try to monitor what's going on there, and otherwise just unmute yourself and ask our presenter directly. Okay. So for the community discussion, I mean, it's open floor, whatever is up your mind. Just unmute yourself and ask. So basically, any questions about ongoing courses, what's happening at the moment, topics you would like to hear more about. So like anything you're particularly excited about, what's happening. Could be what you're working on, anything new that you just spotted and think is sort of like super cool. Projects, papers, whatever comes to mind. So whatever you discovered in the last couple of weeks you think is not newsworthy. So anyone? No one really? I mean, I can maybe start it off with one topic that I think was really gaining traction was definitely Swift for TensorFlow, because that's also going to be the second, the two last lessons in the Fast AI course will be about Swift for TensorFlow, and there's quite some interest, very little documentation yet, very little actual stuff out there, but it seems to be like a lot of people are super excited. And there's also some interest about learning Swift. Like, I guess it's a pretty new language, and a lot of people maybe only know it from iOS development, if at all. So we also started a new Slack topic channel on Swift or Swift for TensorFlow. So if you have any want to discuss any stuff like that, you can post it in this Slack channel. And there's also on Fast AI a dedicated forum that's open to everyone, Hairbrain, that's specifically about the plans for bringing Fast AI to Swift for TensorFlow. So it's very early days, but it seems to be like Jeremy is really keen on it, and there might be some development happening. Anything from you guys?
Hi guys. Can you hear me?
Yeah. Maybe you can speak up a bit.
Okay, can you hear me right now?
Mm-hmm.
Okay, so thank you so much for the meetup. I've been coming around. My name is Steven, by the way, from Nigeria. And I've been coming to the meetup a lot, and it's been amazing. So currently I've been working on something, and I wanted to bring it to the meetup to be able to get inputs and probably maybe know how I can do it better. So I've been working on a project, and it's for tumor images for pathologists, right?
Okay.
Yeah, so I call it cyber oncology. It's basically a deep learning driven software that would help pathologists to make quicker and faster and more accurate diagnosis of different types of tumor, not just making classifications, but also staging it and also trying to recognize the objects in the tumor. Because, you know, tumor images, it's not just enough to say that it's a carcinoma, or a transitional cell carcinoma or squamous cell carcinoma. It's more like, can you tell what's in the picture, what in the tumor image that classifies as a carcinoma, or so more like object detection, right? But I've been looking around for. I've built a proof of concept. It's working. It can make about 80 to 90% accurate classification, but I've not been able to see a research paper that focused on deep learning application to tumor images of different classes and being able to recognize objects. And so my question is, okay, what I'm bringing in, it's are there like methods to that I could use for this kind of project, to be sure that I get not just accuracy on the image and also to be able to recognize different type of objects in the image? I don't know if I'm making myself clear. Or
like what's the thing you're struggling with the most at the moment? A different classification or?
Okay. A classical scenario would be that, okay, because I'm in medical school and I'm in final year in medical school. So usually it takes about 3 days to biopsy a tumor image and then properly stage it. It takes about 3 days to do that. And so, like, I am trying to reduce that work by being able to not just classify a tumor image. I want to be able to stage it too. And I want to be able to recognize the object in the tumor image. Now, that's a little bit hard for me because a tumor image almost all the time looks the same. So I don't know. My first question is, are there any like research papers that anyone knows that I could use? Maybe that because I've tried searching, I've not seen anything on tumor images and object detection in a tumor image like that. And
excuse me, I have a question. What do you mean by stage it? When you say
staging, right? Okay, so in pathology, when you biopsy an image, right? You want to know whether it's stage 1 or stage 2 or stage 3 cancer.
Oh, I see. Okay.
Yeah, so staging, the classification goes like this. For instance, you can say that is a lobular ductal carcinoma of stage 3. So, and there are features in this biopsy and tumor image that makes it possible for you to say that it's stage 3 or stage 1 or stage 2. So, but I've not seen any. I don't know. Okay, I don't know how to go. I don't know how to go about that because that's like what I want to solve. That is my main angle for the problem. Not just being able to classify it because that's like trivial, but being able to.
Okay, but do you have a labeled data set of stages? Like, do you have a labeled data set of images with along with the stage cancer and the type of?
Okay, yeah, that is the new shift I'm making now. But I'm thinking that because tumor images, they almost always look alike. And I thought maybe if I could see a paper or if anybody has a more proper guidance on how I'd go about this so that I don't like waste my time on the wrong track. Yeah.
Hi, Stephen. This is Philip from Germany. I've just heard your story. I think it's very, very interesting. As to your question regarding this paper, are you aware of the paper of Andrew Ng? He did something similar, I think, to your project with radiological images. I will look up the paper and send it in the chat to you. I think that might be in a similar direction as yours. Okay. I read up the work on UNets and like building a UNet to do that and detecting all the objects, but I don't know, it didn't really seem to fit, but I'd love to look at that. Thank you so much. Sure, I will Google it and send it in the chat to you.
Okay.
So it seems like the problem you're doing is real. You're saying it's not just classification, but it seems it seems that it is. I mean, in the sense that you need to classify the type of cancer and the stage, so you have to make 2 classifications.
Yeah, because that is when it makes more clinical interest, it make more clinical sense. Because classifying a tumor, that's fine, but what stage is it? Is it at the point where you got to worry so much or not? Like, because it's gone now. If you just classify a tumor image and tell someone that is a squamous cell carcinoma, you're not really helping. Yeah. You're not really helping because, and I'm trying to give pathologists a second opinion, not just telling them that it is a lobular ductal carcinoma. I want to tell them why I feel like it's that. So I want the machine to be able to, or the network to be able to tell the type of cancer and show the object that is guiding the classification and the staging.
I see.
So, can I suggest that maybe you are you on Slack?
No.
Just join our Slack and maybe open a topic there, and then because I think medical applications are quite interesting, but I'm not sure how many people are experienced there. Maybe you find a couple of more inputs. So if you just join our Slack channel and just go to the deep learning the appropriate channel or channel and just type in what you're planning there, and we can chip in, and then it's much easier and more focused, I guess.
All right.
Also in the Fast AI group, there are several doctors who are interested in medical imaging. So if you search some of the forums and look for comments, you'll find them.
Okay, that's great. That's great, because I want to do that before I get out of medical school. So
sure.
yeah.
No, there should be
like
some people around who know this. Yeah.
What?
There should be some people around in the forums and maybe even on our Slack that did have some experience with medical data. So maybe you find someone who can really help you.
Okay. So how do I join the Slack channel?
It's TWiML.slack.com.
Yeah, or go via the TWiML AI homepage, and I think there's a link.
Okay. Okay. All right. Thank you so
Cool.
much.
From Germany.
I have a suggestion for him, but I don't know if anyone can hear me.
Yeah, in the interest of time, I think we need to keep moving a bit. Maybe connect in our Zoom chat or in our Slack. Like in the Zoom chat, you can interact right now if you want to point something out. But I would.
Yeah, whose question was that?
Come again?
Who just asked the question about medical imaging?
Steven.
Steven, right?
Steven, that's my name. That's my name, Steven.
Yeah.
Can I drop my? Someone is asking if I can drop my contact info here. Can I do that?
Yeah, just open the chat and put in and.
Okay. Okay. All right. Thank you so much. I'll do that.
No worries.
Okay.
All right. I think I don't know. Maybe if someone has a shorty, we can put it in. Otherwise, I would ask you guys that we move to the main presentation. Anyone else? Something concise and pressing that we want to discuss? No. Okay, then I would say we start with the main presentation. I will end my screen sharing, and Sam, you should be able to share yours.
Just a minute.
Okay, Sam, can you grab the screen and show your slides?
Yeah, can you see my screen?
Yeah, coming up.
Okay, sir. Hey, hello everyone, and a very good evening. Yeah, so I am Samujjval. You can call me Sam. So I am a PhD student at IIT Hyderabad in India. So my research area is mainly like multi-level supervised classifications. So this is, I'll be talking about matching networks for one-shot learning. This is kind of a very important paper in the area of one-shot learning. So this was published in 2016 NIPS by DeepMind. So first, to start with the paper, I'll just give a little bit about the abstract, like what is the paper about. So basically, they used one-shot learning with attention and memory. I'll define what is one-shot learning, how the attention is used, and how the memory is used. And basically, this paper has two kinds of contribution. First one is a model architecture for one-shot learning, and the other contribution is they proposed a new kind of training strategy which goes very well with the one-shot learning scenario. So like uniform training and testing strategy. And because of this, like they're kind of trying to utilize both parametric and non-parametric learning approaches. So both has some like trade-off. So they are kind of trying to take the best of both worlds. And so like the architecture can be summarized as such that it's kind of, although the original authors didn't coin this term, the term is coined by Andrej Karpathy in his notes about this paper. So he called it differentiable nearest neighbor. So basically differentiable nearest neighbor works like taking the advantage of both parametric and non-parametric models. So using this matching network, they improved the accuracy of ImageNet. So basically, they didn't exactly run the whole code on the whole ImageNet. So they created three subset of it. One is called mini ImageNet, another is called dog ImageNet, another is called rand ImageNet. And using they showed that the accuracy increased from 87% to 97%, and there is another data set called Omniglot. There also they improved the accuracy. Okay. So basically, let's start with supervised learning. In traditional supervised learning, test levels are used during training. So what do I mean by that? This like the label space is same for training phase and prediction phase. So here in the training phase, you have the labels airplane, automobile, bird, cat, and deer. So you learn a classifier on these label space, and you for a new sample, you predict on these label space only: airplane, automobile, bird, cat, and deer. But in case of one-shot learning, that is not the case. In case of one-shot learning, you can, in training phase, you have the label space like dog, frog, horse, sheep, and truck. So you learn a classifier on this label space. But when predicting, you will be predicting on the right image, like right side image, like airplane, automobile, bird, cat, deer. If you see that there is these two sets are completely disjoint. So, but although these two sets are disjoint, there is another set on the right image. So that with labels with the same level which you want to predict. So those are called supports. So I'll tell you, I'll discuss the idea behind the support. So basic idea of one-shot learning is like, let's say I show you what basically how humans learn. So like you will be shown a single image of zebra, let's say, and you can understand what zebras are basically made of. And you can see, like you can categorize any other zebras from other non-zebras. So like this idea of just seeing only one example and learning from that, that is the basic crux of one-shot learning. So so basically in one-shot learning can like, this is like domain of learning strategies. So this is basically, you could say like N-way K-short learning. So let's say you have a on the left side you have a training data set, and on the right side you have the testing data set. Here also the both of the level space are disjoint. So you have a training task which comprises of the training data set, and you have a testing task which comprises of the testing data set. Now, during the testing time, you choose a set of labels from the testing task. It could be equal to the size of the testing task also. Here the testing task size is 5, but here for simplicity you are just taking three level. So, and for each level you are taking single examples. So this is what is called support set. So these are the examples you get to see for each of the categories you have chosen. But the query will be from these one of these level set, like from this L prime. So this is the basic. In this case, actually, if you see, this is three-way one-shot learning. Why three-way? Because the level space is made up of three levels: automobile, cat, and deer. And for each of the levels, there is only one sample. That is like either one car, one cat, and one deer. So you'll have to predict for a new sample for two automobile, cat, or deer. So this is called three-way one-shot learning. It could be like you can take 20 levels, and for each level 5 samples. So then it will be called 20-way 5-shot learning. So in this paper, basically we'll look into one-shot learning. So as I said previously, the contributions are twofold. One is matching networks, another is training strategy. So I will start with the matching network, then I will go into the training strategy. So matching network is basically, the idea behind matching network is like in case of why do like parametric models usually take so many samples to learn. So for each of the classes, parametric models actually learn the properties of each of the classes using lots of samples into their parameters. But in case of non-parametric learning, not all, but in few of the non-parametric learning, one of them is k-nearest neighbor. you don't need any learning as such. You don't need any training. So you can just project it to some space and find the nearest sample, and you can just propagate the level from the nearest sample to the to your test sample, and you can just give that as your predicted level, right? But the problem with this non-parametric KNN is that when you are projecting it to some space, what kind of metric you are choosing to define the similarity? How do you define the nearest neighbor? So that actually matters a lot. So here in this matching networks actually try to solve both of the problems. So it's kind of a parametric model. Yeah, is there any question? Okay. Yeah, so it's basically a parametric model, but the parametric model only works to define the metric. So once the metric is defined on the once your nearest neighbors, how you define the nearest neighbor is done, then you don't need the parameters anymore. So let's see how it is done. So basically, so it works on two fundamental points. One is called full context embedding and attention kernel. So I'll discuss. I'll start my discussion with full context embedding. So in full context embedding, so basically here the two matching nets has two inputs. One is called supports, another is called targets. So basically, although here I'll be calling them as targets, in the paper it's not mentioned as targets, it's like samples or something. So supports are embedded in such, so here in the matching network you are using a cosine distance. Here the distance is fixed, but you are changing the embedding so that the similar neighbors which are nearest should, because of their embedding, should come to a closer in their embedded space. So here the idea is take each of the supports and embed them in such a way that it's all the other supports are also encoded in this. So for each support, each sample in a support, basically you are embedding all the other supports present in that support set. So this is done via a bidirectional LSTM. So here, if you see the first equation, so G is basically Xi's are the supports you want to embed, and Xi is basically an element of S. S is the support set. So each of the Xi is passed through a G prime function. So G prime function is basically any pre-trained embedding. You could take inception net or VGG net or any other thing. So you will get some embedding after passing through VGG net or inception net, and then you run it through the LSTM. And when running it through the LSTM, you encode the Xi along with its supports. So the new Xi which you get is basically a combination of G prime Xi and all the other samples present in that particular support set. So if you change the support set, you will get a new embedding. So for even like if you change the ordering of the support set, you will get a new embedding. So although the ordering part is not mentioned in the paper, but in general, in case of LSTM, if you change the ordering, you will get a new embedding. So, but according to the paper, looks like they have like taken it into account that ordering is random. So they haven't mentioned anything specific about the ordering within a particular support set. So this is the way to embed the support set. Then coming into the this is how it looks like. So all this, let's say there is a data set which comprise of only pictures of different types of dogs. So let's say this all the pictures will be passing through a G prime function. So that's like a kind of VGG net or some other network. Then it will pass through an LSTM, and this LSTM is connected. This LSTM will connect all the other samples in that particular support set, and I will get a embedding which is a kind of a combination of that particular image and all the other images in that particular support set for each of those samples. So you are trying to capture the nearest neighbor so basically you are considering that whichever samples supports are present in the support set, they are kind of nearest neighbor. So you are trying to capture the nearest neighbor into the embedding itself. So this is
Sam,
the.
can I ask a quick question?
Sure.
So what's the output of G prime here? Like, is that the predicted class label, or is that something earlier in the network, like the features that it's learned?
Yeah, it's so G prime is basically the VGGNet. Let's say it's VGGNet. So you pass it through the VGGNet. You get the VGGNet is already pre-trained. You'll have to imagine it's already pre-trained. You pass it through the VGGNet, and whatever embedding you get, that is used as an input to this matching network. Okay.
Okay, makes sense. Thanks.
Yeah, welcome. Okay, so this is another part. So this is second function, which is called, so in the paper it is mentioned as F. So this function is basically used to embed the targets. Targets means for which you want to predict. So one thing I should reiterate again. So for the supports, you have the level information. You don't need the, like it's not hidden. But in case of targets, the level information is not present. So you'll embed the targets in such a way that the samples present in the support set, that is also encoded in that target. So how do they do it is basically like this. So they use by a bidirectional LSTM here also with attention. So here, although in the paper they mostly use bidirectional LSTM, but it's not necessary that you should use bidirectional LSTM only. You can use anything. So like that's like kind of open in this area. So they define this LSTM in such a way that again F here is F prime is basically again some VGGNet or inception net. You take the output of that particular network and pass it through an LSTM where the hidden network is hidden. Excuse me. Hidden cell is defined in such a way that basically you define the hidden cell is as a combination of just a minute. Yeah, let me just check my notes here. Yeah, so basically here you try to take the relevance of the support sets, samples in the support set, and use that relevance as a attention. So how do you get the relevance? So basically relevance is calculated here in the third equation. So here A is the attention. So attention is defined as softmax of hidden state multiplied with samples in the support set. So when at the very beginning, this is like these equations are given after k iteration. So at the very beginning, where a hidden state is like h1, so then the g of xi is not embedded in it. So you take the simple h1 and you take the g of xi, multiply them, and you will get a scalar, and that scalar will work as a attention value, and that attention you multiply with each of the corresponding attention you multiply with the corresponding support set sample, and you will get a embedding of samples of support set with their corresponding relevance. That relevance you use along with the hidden state in the next layer. So you merge both of them, and so from the next okay, let me just show you the pictures, it will be clearer. So so this is how the network looks like. So you get the supports from the G prime, and you and then pass it through the G, and you will get the G of xis, and you take the hidden state h in the beginning it will be h of 1, and you multiply h of 1 with each of the gxi's, and you get some relevant score, and you take that relevant score and take the weighted sum, and you will get the whole relevant vector for the whole support set, and you then you use that as an input to the next iteration of the LSTM. And in this next iteration hk, basically you like basically in the initial time it will be h2. So in h2 you get an LSTM embedding where the relevance and the supports are also included. So f is basically a function of two things. One is x prime. X prime is basically the test image, and s, because s is basically the support set. So when you are taking this g inputs, so that can be considered as s. So hk is basically you could say that output for the f function. So if you hk minus 1 will be like previous level, and initially when it is h1 there will be no support included in it. Does that make sense? Okay, I'll carry on.
So I need a bit to wrap my head around, but I can't really pinpoint where I'm stuck.
Okay.
But maybe yeah, it's a complicated topic. Maybe it gets a bit clearer when we progress.
Yeah. So okay, let me just reiterate it a little bit. So the bit complicated part is like the equation is in the paper also is given after kth step. So it's not from h1 to h2 like that. So in the initial state, you don't have any support information embedded in the LSTM, but you take the h1, multiply with all the supports, you take the relevant score, and then again use that relevant score as a attention, and multiply those relevant score use that attention on the supports again. So basically in this equation where rk minus 1 is defined, so this attention of hk minus 1, if you take like the first iteration, it will be h1, multiply with g of xi's. So all the xi's cardinality of s, like for all the supports you multiply them, and you will get a relevant score for each of the supports and multiply them along with their that particular supports embedding. Okay.
Okay, and the size of the support set is like 3 in this case, right? Because 3 dogs, and that's
yes.
It's hard to imagine that it's enough to inform the model, but maybe, I mean, apparently it works. So
yeah, so you can actually it's not exactly that you have to fix to 3 only. You can decide, but although it has in the paper it has a limit. So like the minimum support set they have used is 5, and the maximum they have used is 25. So like okay. Yeah, so like they used like total 5 types of classes, and for each of the classes you either take 1 sample each or 5 sample each.
Okay.
Yeah.
All right.
So this attention was used only for the embedding, full context embedding on the f functions. Then there is another attention which is actually used for all the samples. So there is a picture in the below part, next part, so it will be clearer. So it works like this. So you predict based on, you take the attention of x hat and xi. So here xi comes from the supports, and x hat is the target which for which you want to predict, and then multiply the attention along with the supports levels representation. So although it is not mentioned in the paper, but the level representation is actually 100 encoding of the supports. Okay, so in some sense you could think of it like this. So prediction is basically a linear combination of levels in the support sets. So for each target, you let's say first support belongs to class first class. So its one hot embedding will be like 100. and second support belongs to class number 2. So it's one hot embedding will be like 0, 1, 0, and the third one belongs to class number 3. So it will be like 0, 1, 0, 0, 1. So you take the attention. Attention here is basically defined as the softmax function of cosine similarity of their embedding. So here f of x hat is basically the embedding of x hat, and g of xi is basically the embedding of xi. And you take the cosine distance between them, and that acts as a attention between the x hat and the xi's. So that cosine distance is basically this value 0.2 or 0.5 and 0.3, and you multiply the support set one hot embedding, and you will get something like a vector which will be like because of the softmax function, it will be like a probability distribution, and you can take the highest probability as the output.
Okay, yeah, that makes it much clearer. That's good. Thanks.
Yeah. So basically, they trained this network using a cross entropy loss, and one more thing, so although the authors use cosine distance, so you can use some other distance also, not necessarily you will have to use cosine distance only. So this is how the network looks like once you have the G and F. So basically you get the support set xi's, and you take the x hat, pass it through F, you get f of x hat and s, and you take this, you pass them through again another attention. This is the like model level attention. So this attention will give you the similarity between the x hat, which is a test sample, along with the supports it has in that particular set. So you will get a vector for each of the classes, and then you multiply the one hot vectors of each of the classes, and whatever like maximum you can predict as the output. So like this is the same architecture with the equations. So here you are basically using cosine similarity, then pass it through a softmax function that will give you a attention. Then use that attention function between the x hat and the xi's, and when you have the similarity between x hat and all of the xi's, then take that and multiply with corresponding yi, basically one hot embedding, and you will get a probability distribution over the level space, and that will be your final output. Okay. So this is the basic idea of matching networks. So there are even like you can use CNN and other things also. Yeah, is there any question? Okay. So this is the second part of the contribution of the paper. So they actually come up with a training strategy. So this is kind of like a interesting, like, so in that initial part when I describe one-shot learning, I described how the testing phase works, right? Prediction phase. So they tried to replicate the prediction phase exactly same to the training phase, and for some reason people did not do that before this paper. So this is like kind of, this is how it should be done, but previously people were using some other approach. So like same as the one-shot learning approach, you take it instead of the testing task, you take the training task, you choose a set of labels, and you create the support set from that particular set of labels, and you choose another set of batch, and that here in the paper they are called as batch. So batch is basically the same thing which I called as a target. So whatever I mentioned as target is basically the batch in the paper. So you from the label set L, you create two batches. One is for support set, another is for the targets. So in the support set you have the level information. In the batch or targets you don't have the level information. So this is kind of like exactly similar to the one-shot learning prediction phase, and like but before this paper, nobody did that. So they actually tried to do it like a normal supervised learning approach, and then applied one-shot learning in the prediction phase only. But in this paper, they applied one-shot learning strategy in the training phase also. So this is the second contribution in their paper. Okay, so this is the data sets they have used and the results. So they basically tested on 3 data sets, Omniglot and ImageNet. So ImageNet has basically 3 different subsets: mini ImageNet and ImageNet Rand and ImageNet Dog. I'll describe in the later what does they mean. And there is one language modeling task that is called that is done on the Treebank data set. So in the Omniglot data set, so it's basically a combination of 1623 different characters, and each of the characters has 20 different, each of the characters was written by 20 different person. So each class has 20 samples with them. So in this case, so they basically used compared their network with the convolutional Siamese network, and there is another network. I haven't been through the related work section much in detail, but like you can go look into the paper for that part. So they showed that with for some weird reason, actually without the fine tuning, their accuracy is better in most of the cases, and full context embedding didn't help much in these cases, and baseline and Siamese network actually with fine tuning they improved, but in case of matching network with fine tuning, like they kind of decreased a little rather than improving for some reason. It's not actually mentioned why it happened. This is for the Omniglot, and this is for the ImageNet. So ImageNet has the 3 parts. This is called the mini ImageNet. So from the ImageNet, they created a subset of ImageNet with 80 classes for training and 20 classes for testing, and they found that their model with fine tuning and full context embedding is basically working a little better without. So the last 2 rows are basically with full context embedding, and the second to last rows are without full context embedding. So like it improved the accuracy like 2 to 4%, and fine tuning also improved a little. So full context embedding shown little effectiveness in this case, but not much. Then there is 2 other data sets. One is called Rand ImageNet and another is called Dog ImageNet. So Rand ImageNet is basically comprised of random classes, 82 randomly selected classes, and for training, and remaining classes 118 classes for testing. But in case of Dogs ImageNet, all the non-dogs classes are selected for the training purpose, and only dog classes, like subspecies of dogs, are chosen for the testing purpose. So testing sample only has dogs, nothing else. But if you see in this case, so that matching net is basically doesn't do better in case of one-shot learning in the dogs data set. So one of the one of the reason that matching net is not working better than the inception classifier, they mentioned is like because in the dogs image net, so testing only has dogs and training has except dogs everything. So basically the distribution between training and testing is very different. So that is a kind of a challenge for matching net. If the training and testing distribution are very different, then matching net doesn't work well all the time. So okay, so this is the pen Treebank. So they kind of defined a new task for this operation. So the task is something like this. You have a set of sentences. From each of the sentence, one word is missing. So that particular missing word is basically the label. So here you have 5 sentences, and each of the missing words is like this. In the first sentence, prominent, the word prominent is missing. In the second sentence, the word series is missing. In the third sentence, the word dollar is missing. In the fourth sentence, towel, and fifth sentence, comprehensive. And there is one query sentence. There is also one word missing in the query sentence, but this missing word will be either of these 5 words. So this is how we define the task in the language modeling case. So in this case, so basically they compared their result with the Oracle LSTM language model. So here the Oracle LSTM basically means that it has seen all the words present. So it has everything, like not words one shot. Like Oracle is basically the upper bound of the scenario. So like it has seen all the words, then predicted. And in case of one shot, it haven't seen those words and then tried to predict. So MatchingNet works pretty well. It's like for one shot, it's like 32.4% accuracy. For two shots, 36.1% accuracy, and 3 shots 38.2% accuracy. So like if you increase the number of samples present, the accuracy usually increases. And in conclusion, so the non-parametric structure gives the matching networks like the ability like to learn from single samples only. You don't need like thousands of samples for matching networks to work. It's basically to summarize the model, it's like a trainable end-to-end differentiable nearest neighbor with metric learning capability. So it works very well in 3 different data sets. And training a model, they propose the training phase also like a one-shot way makes the learning easier. Before this paper, like for some reason researchers didn't use the same training and testing phase. So like they use the traditional training procedure, and then the testing phase that they use the one-shot learning way. But they this paper changed that one. So this is few of the remarks from my side. This is not mentioned in the paper. So like this is basically in summary, like they introduced the matching networks. And so from the you can see this paper in few different perspectives. So if you see from the parametric perspective, you can say it like it's basically a paper of metric learning. If you see from the non-parametric perspective, it's basically a KNN where the label predictions are linear combinations of nearest neighbors in the support set. And another part of this paper is training and support set level distribution should be close, as we've seen in the dog ImageNet case. If the training set and testing set supports are not very similar, distribution are very different, it might not work well. And one other thing which is not mentioned in the paper is that when you are passing the samples through the FC, the ordering of the samples are not mentioned to have any significance, but in usually have a significance. Let's say if you in the f function, if you give a if you want to embed the x hat, but the ordering of the support is like x1 to xk to xn, and there is another ordering that xk is in fast, and then x1 and xk are swapped kind of, and then the embedding you will get will not be similar to the first one. So this part is not like taken into account in the paper. So this could be like a study about this would have been much interesting, like how the ordering affects the accuracy or effectiveness of the model. And one of the limitations of the paper is kind of like sample size during the training and testing are fixed. It's like minimum is 5 and maximum is 25. Like for all the operations, it's kind of fixed. They haven't changed it. So if the it's not very suitable for, like, if the training set is grows like online, then it might be a bit problematic to formulate the problem. How do you create a batch and how do you create a level state, all these things. And if you see into the details, like when calculating the attention, so like if the support set becomes very large, it will become computationally expensive. Okay, so this is all my observations about the paper. And these are the kind of resources. There are many blog posts by different researchers about this paper. This is kind of a very well-known paper, and like and many versions of the code is also available. Like you can go to the papers with code and search for this paper, and you will get like 5 to 6 different implementations, including PyTorch and TensorFlow and Keras and others. And these are the references of the important references of the paper. There are many other references included in the paper. That will be all.
Well, thanks very much. Very interesting talk and paper. It's pretty heavy, I think. If you haven't been into attention networks at all, then it's a bit daunting. But I think I kind of grasp the main features of that. And like, to me, it's always like really hard to imagine that with a couple, with like really low number of samples, that you can actually achieve something. But this example that it's like a linear combination of like weighting of the scores, that kind of hit home with me. That kind of makes sense to me. So I think I'll definitely, I haven't had the chance to really read it before, but I think I'll definitely do that. That sounds like a really important.
It's very interesting paper, in fact.
Yeah. Any other comments? We are almost at the hour, but anyone?
Thank you very much, Sam. I want to second Christian. I also want to dig in the paper now. I think it was very interesting what you presented. So thank you very much for that. I was thinking about the kind of, if you think about it, it's kind of intuitive, the one-shot learning approach. I was thinking if there is even a biological plausibility to it, because if you think about it, how children learn, they basically, do they, or that is my question that I have, do they really learn by one-shot learning, or is it basically like repeated sort of training examples from their parents, really, and then they sort of conceptualize the concept of, say, a banana or something like that?
Okay. So to answer this, okay, let me give you a scenario. Okay, so let's say I showed you a picture of a zebra. Okay, and then I told you that zebra is a zebra with red stripes. So you can easily recognize pictures of zebra, right?
Now I see. Yeah, right. That makes sense. Yeah.
So this example is actually mentioned in one of the blog posts. So I just gave that example.
Yeah.
Any other questions, comments, anything?
No, all in all. If there's no further questions or comments, I mean, we can also like discuss later on Slack or in the coming days if there's like stuff coming up. All for like if there's dedicated questions to one of our meetups, we can like make a deeper discussion there as well. And I would say thanks again to Sam for this, I guess, hard work.
Welcome.
And so I would close it out for today, and we will convene again at a fixed time, and we will make sure that it's clear to everyone which one, starting of May. So thanks everyone for attending, and see you next time.